October 13th marks exactly 1 year since Flight 5's breakthrough, and SpaceX just revealed Flight 11's complete timeline. This is the final V2 test before version 3 takes over. Ship 37 and Booster 15 won't be caught by the tower. Both splash down as SpaceX extracts maximum data. The stakes: 24 reused Raptors being pushed to their limits, intentionally removed heat tiles testing failure points, and a new 5-engine landing sequence critical for V3. Every decision here directly shapes the future. What makes this mission so vital? Let's dive right in. October 13th, 2024. Flight 5 achieved the first full-duration Starship burn. October 13th, 2025. Flight 11 launches exactly 1 year apart. SpaceX doesn't do coincidences. They operate on engineering timelines, not symbolic dates. The 6:15 p.m. central liftoff confirms their intention. Daylight landings for both stages mean maximum visibility. Every maneuver captured in perfect lighting. SpaceX is turning an engineering test into a public demonstration, and they're not playing it safe. Flight 10 exposed a critical flaw. A middle ring engine failed during ascent. SpaceX's response? Booster 15 now carries 24 reused Raptors. Not refurbished, reused. This is deliberate risk-taking. SpaceX knows this booster won't return to the tower. They know Ship 37 is expendable, so they're conducting a destructive stress test. How far can reused engines be pushed before failure? The middle ring engines are critical. During the landing burn at 6 minutes 20 seconds, these must fire in perfect coordination with inner ring engines. One failure could cause the booster to tumble. Flight 10 proved middle ring reliability affects everything downstream. Here's the strategic insight. V3 depends on rapid reuse, engines flying multiple times per week. Flight 11 tests that future with hardware they can afford to lose. The data gathered here determines V3's operational limits before the first V3 vehicle ever flies. Previous flights dropped from 13 engines directly to 3 during landing. Flight 11 introduces a critical change, 13 to 5 to 3. The math explains why. Running 3 engines when one fails means losing 33% of thrust instantly. Catastrophic. Running 5 engines when one fails leaves 80% thrust. Manageable. The booster compensates and safely transitions to 3. This isn't about Flight 11. It's rehearsal for V3 tower catches at Starbase. When Super Heavy approaches the launch tower with millimeter precision, engine failure can equal mission failure. The 5-engine buffer provides the reliability margin SpaceX needs. The configuration matters. 3 inner engines plus 2 middle ring engines. SpaceX is specifically testing those problematic middle ring engines during the most critical flight phase, hunting for failure modes under maximum stress. Flight 11's riskiest decision, SpaceX intentionally removed heat shield tiles from Ship 37 before launch. At 47 minutes 29 seconds, Ship 37 hits re-entry. Plasma temperatures exceed 1,400 degrees Celsius. Those missing tiles create gaps where superheated plasma penetrates directly to the steel structure. Why sacrifice a vehicle this way? SpaceX needs to know exactly what happens when tiles fail. Previous flights lost tiles unexpectedly. Flight 11 loses them deliberately, with sensors monitoring every millimeter. Where does structure fail first? How fast does damage spread? What's the minimum tile coverage for survival? This is systematic data collection through controlled destruction. Flaps might burn through. Structure might breach. The vehicle might not survive to splash down. That's acceptable. V2 hardware is expendable. The data protects all future vehicles. At 2 minutes 30 seconds, something happens that will never happen again. The hot staging ring jettisons into the ocean. 8 successful flights prove the concept. During separation, Ship 37's engines ignite while still attached to Booster 15. The ring protects the booster from engine blast, then detaches and becomes debris. V3 eliminates this entirely. The hot staging capability integrates directly into Super Heavy structure, permanent, reusable, no jettison. Flight 11 marks the last time SpaceX throws away hardware mid-flight by design. This retirement is strategic. Every jettison loses mass that could be payload. V3's integrated design improves reusability and reduces complexity, but it must provide the same protection without the release mechanism, a harder engineering challenge SpaceX has now solved. At 18 minutes, the payload bay opens. 8 simulated satellites deploy over 7 minutes. SpaceX tested this on Flight 10, but Flight 11 refines the operational sequence. The stakes: Starlink 5, 3 satellites are coming, larger, heavier, more capable. Starship can deploy up to 400 tons to orbit, but only if the mechanism works flawlessly. At orbital velocity, any contact with the doorframe damages satellites worth millions. Each test validates the dispenser system, alignment mechanisms, and deployment timing. SpaceX is also proving they can handle complex choreography: multiple satellites, different orbits, different deployment windows. This capability attracts commercial customers, NASA, DoD, private companies watching for operational reliability. At 37 minutes, 48 seconds, one Raptor reignites in space. This brief burn validates a capability that makes advanced missions possible. Restarting engines in microgravity is complex. Fuel floats, oxidizer separates. The engine must ignite reliably despite these conditions, or high orbits, lunar trajectories, and Mars become impossible. Lunar Starship missions require multiple restarts, igniting in low Earth orbit near the Moon, for descent, for ascent. Each must work perfectly. Flight 11's single restart proves the concept for missions demanding a dozen. Flight 11's most ambitious test begins after re-entry. Instead of heading straight down, Ship 37 performs dynamic banking maneuvers at subsonic speeds, simulating the exact flight path for returning to Starbase. At the 1-hour mark, Ship 37 slows to transonic speeds. The flight computer activates guidance algorithms designed for precision landing. The ship banks left, banks right, adjusts altitude, testing control authority at low speeds. Landing at Starbase requires navigating to specific GPS coordinates with centimeter precision, hitting the tower's catch arms exactly. You can't test that over ocean without simulating the maneuvers first. These banks validate the control systems guiding future ships back to launch sites. How responsive are flaps at low speed? How accurately can the computer predict landing points? How well does Starship compensate for wind and weight variations? At 1 hour, 6 minutes, 14 seconds, Ship 37 flips vertical. 3 sea-level Raptors ignite for final descent. It's the exact sequence a Starbase landing will follow, except instead of catch arms, there's ocean. The timing, throttle profile, and vertical velocity are all calibrated for future tower catches. SpaceX is perfecting the landing approach before attempting the catch. At 1 minute, 2 seconds, Starship passes through max Q, maximum aerodynamic pressure. This is when atmospheric density and velocity create peak structural stress. Earlier flights revealed an unexpected connection. How Starship handles max Q affects everything later. Vibrations during ascent can damage tiles, stress welds, and create failures that only appear during re-entry. Flight 11 faces additional stress because of its mass. Ship 37 carries test satellites plus full propellant. Booster 15 pushes harder to compensate. More force, more vibration, more stress on every component. Watch telemetry during this phase. Any anomalies here, unusual vibrations, unexpected forces, could explain issues appearing later. Max Q has become a diagnostic checkpoint as much as a mission milestone. Understanding what happens in those final minutes reveals how precisely Starship operates. T-minus 53 minutes. Liquid methane flows into Ship 37 at negative 161 degrees Celsius. The tanks are structural elements. As they fill, the vehicle's rigidity changes. T-minus 45 minutes. Liquid oxygen follows at minus 183 degrees Celsius. The extreme cold keeps these incompatible substances stable. Temperature differential creates thermal contraction. Engineers must account for in every calculation. T-minus 41.5 minutes. Booster 15 begins methane loading. With 33 engines and massive tanks, the booster requires precise filling to maintain balance. T-minus 33 minutes. Booster oxygen loading begins. The orbital launch mount now holds 4,600 tons of vehicle and propellant. T-minus 10 seconds. Water deluge activates. Thousands of gallons per second spray across the mount. Without this, acoustic energy from 33 Raptors would destroy ground equipment. T-minus 3 seconds. All 33 Raptors begin ignition. They don't fire simultaneously. Each lights in rapid succession, building thrust in a controlled wave. T0, 74 meganewtons of thrust. Nearly 17 million pounds overcome gravity. A 400-foot rocket rises, slowly at first, then accelerating rapidly. This sequence repeats every flight, but Flight 11 executes it with 24 reused engines. Every ignition tests reusability under operational conditions. Step back and see the pattern. Every Flight 11 choice validates something V3 requires. 24 reused engines prove rapid reuse reliability. 5-engine landing sequence provides redundancy for tower catches. Missing heat tiles expose failure modes and minimum protection needs. Final hot staging ring validates the old system before V3's integrated design. Satellite deployment demonstrates operational readiness. Engine restart enables multi-burn missions. Subsonic maneuvering tests precision landing guidance. Max Q data validates structural design under peak stress. This isn't just testing, it's systematic validation of every V3 capability. Ship 37 and Booster 15 are deliberately pushed beyond normal limits to expose weaknesses before they appear on operational hardware. SpaceX is sacrificing 2 complete vehicles to buy certainty about the next generation. The cost, $100+ million in hardware. The return, data that prevents V3 failures worth billions. Every sensor reading, every telemetry point, every camera frame feeds into V3 design reviews, manufacturing processes, and operational procedures. Flight 11's failures become V3's improvements. Consider the heat shield test. If tiles fail catastrophically during Flight 11, engineers know exactly where to add protection on V3. If structure survives with missing tiles, they know they can reduce mass. Either outcome is valuable. The reused engine test follows the same logic. If 24 reused Raptors perform flawlessly, rapid reuse is validated. If engines fail, SpaceX identifies the actual reuse limits and adjusts V3 maintenance schedules accordingly. SpaceX scheduled 6:15 p.m. deliberately for media impact. Daylight splashdowns photographed beautifully. Evening hours maximize U.S. social media engagement. Public support drives funding, regulatory approval, and political backing. The live broadcast starts 30 minutes early, capturing fueling. Venting plumes of methane and oxygen create dramatic visuals around the launch tower, perfect for viral content. Every camera angle, every tracking shot, every engine close-up is calculated to inspire. SpaceX needs the world watching when V3 debuts. Flight 11 builds that audience. Flight 11 represents a turning point. It closes the V2 chapter while opening the V3 era. Every test, every risk, every data point gathered here shapes the future of human spaceflight. The symbolism of October 13th reinforces this transition. 1 year ago, Flight 5 proved V2 could work. Today, Flight 11 proves how far V2 can be pushed. Tomorrow, V3 takes over with the lessons learned. When Ship 37 splashes down at 1 hour 6 minutes 30 seconds, it marks the end of an era. But it also validates the beginning of rapid, reliable, reusable spaceflight. The kind that enables lunar bases, Mars colonies, and orbital infrastructure. That's what makes Flight 11 historic, not just what it achieves, but what it enables. This is why October 13th matters. Flight 5 proved V2 works. Flight 11 proves V2's limits. 24 reused engines, exposed heat shields, 5 engine landings tested to failure, so V3 avoids them. The result? V3 eliminates disposable parts. Tower catches enable rapid reflight. Proven reuse makes orbit routine. Testing becomes operations. Ship 33 and Booster 13, first V3 hardware, are at Starbase now. Within months, the first upper stage tower catch. Within a year, weekly flights. Lunar and Mars infrastructure isn't theoretical. It's being validated today. My question, when V3 attempts that first Starbase catch, will SpaceX succeed immediately or need multiple tries? Comment your prediction. This is Space Hub. Real space engineering, no hype. If this breakdown clarified what Flight 11 tests and why V3 matters, hit like. Subscribe and enable notifications for V3 coverage. That's when everything changes. The future is being built in real time. We're tracking every step,